Good evening, everybody in the UK, and good morning, people elsewhere. This is Larry Banks speaking. Welcome to this Institution of Structural Engineers webinar. I will be sharing the platform with Kieran Ruane, who's at Munster Technological University in Cork, Ireland. I am at Georgia Tech in the United States. And the two of us are representing the Rewind Network, which is a group that was set up maybe 5 years ago that includes Georgia Tech, City University of New York, University College Cork, Queen's University in Belfast, and Munster Technological Institute, formerly known as Cork Institute of Technology. I'll just give you a quick outline. I'll talk to you a little bit about what the Rewind project is, briefly, and then go into the topic, which is blade repurposing, what to do with decommissioned wind turbine blades, which are causing problems with disposal, basically. We'll talk about codes and standards from an engineering perspective, how we can design with them, structural engineering analysis and design. We'll talk of 3 example projects, the blade roof, blade pole, and blade bridge, but mostly about the blade bridge, which Kieran will talk about and has been most actively involved in the design. And this is a bridge that will be installed almost as we speak in the next week or so. I just want to check that everybody can hear me because I can only see my own screen. Anne and Kieran, is everything coming through okay?
Yeah, everything seems okay on my side, Larry.
Okay, I will continue then. The Rewind project, as I say, is the university involved. It was set up about 5 years ago under what is called the US-Ireland Tripartite Research Grant, which funds cooperative research between academic institutions in the United States, the Republic of Ireland, and in Northern Ireland. We have also received funding from the New York State Energy Research and Development Agency, and then Science Foundation Ireland, Department for Economy in Northern Ireland, and NL Green Power. Currently, the project partners are Logisticus Group, who is a decommissioner in the United States, NL Green Power, a major international energy provider with renewable energy as well. Siemens Gamesa, who's a large manufacturer of wind turbines. Cork County Council, which we hear about, the New York City Department of Design and Construction, and there is an International Energy Agency, Task Group 45, which is currently preparing a large report on recycling and reuse and repurposing of wind turbine blades. As part of our activity, we've done a number of ideation workshops to develop blade repurposing concepts, and then to bring those concepts into some engineering reality through extensive virtual, if you will, analysis, not just renderings. So the first one was in 2018. We produced a design atlas, which can be downloaded from our website, and we've just recently completed our 2021 catalog. These are just some of the concepts, and these are some of the things that you would see in our catalog. They're renderings, generally, of the concepts, but they actually use real geometries of actual blades. So these are actual blades that have been rendered into various situations, housing, bridges, poles, barriers, for example. Many, many other concepts that many around the world have thought of as well. Just to give those of you who are not familiar with the wind blade technology, the wind blade, of course, is the wing of the propeller, those 3 bladed turbines, which are the common ones these days. And those are the energy capturing devices that turn the generator and the turbine. So this, for example, is the first wind farm that I visited maybe 6-7 years ago. And this is in upstate New York. This is a Vestas V82 blade, which is about 40 meters long. This is a very, very small blade at the moment. So you might have heard in the news that now turbines up to 15 megawatts are being built, mostly for offshore. And these are going to be over 100 meters long. So 2.5 times really the length of this blade. That's me standing at the tip. This blade perhaps has a cord. The maximum cord is that center where you see that power transmission pole in the middle, the widest part of the blade when sitting upright, edgewise we call this. What's inside a blade? Well, the inside of a blade is quite interesting. A blade is hollow. It's a hollow tube. It's not unlike an aircraft wing. All of these blades are made of fiber reinforced composites. 99% are glass fiber reinforced composites. The early blades were glass fiber reinforced polyesters, and nowadays they're mostly glass fiber reinforced epoxy systems. Some carbon fiber is used in some parts of the blade, but very little at the moment. As you can see there, we have two basic designs that are used. We have what is called the spar box, which is the box shown with the two webs and the thicker region above. Let me move my pointer up here if I can. This thicker region up here is what we call the spar cap, and that is primarily unidirectional glass fiber reinforced composite material, and maybe, as you see there, upwards of 50 millimeters thick. The other common design is a single I-beam design, which has a similarly very thick spar cap, has a web which is foam reinforced. Here you can also see the foam reinforced in the box spar, slightly different design. Both of these have leading and trailing edge. This is called the leading edge shells. And these cells are sandwich composites. In this case, balsa wood, but also foam may be used. You can see the differences in design. This is a larger blade, and this is a smaller blade. I would say most of the older blades are the box spar. This I-beam design started coming in about 2005. So anything in the early generation from the late 80s up to the 2000s, probably going to have this box beam design. Most of these are made in two halves and then bonded together at the trailing edge and at the leading edge. And the box spar or the I spar, the web is bonded in. You can see the adhesive bonding here. From inside, it doesn't look very pretty. From outside, it looks very pretty, and the outside surface is finished to an extreme, to maybe a 5 millimeter geometric accuracy with various sanding and painting operations. Just to give you an idea of what this looks like along the length, I'm sorry if some of the images on the right look a bit light, but the blade tapers and twists. It tapers lengthwise along the length and widthwise, as you can see in the upper left and the lower left. This is along the length, and this is through the looking down the width. And the profile changes from a circle at the root, where the blade is attached to the hub, through a transition region where the blade changes from the circular cross-section into an airfoil cross-section, and from probably maybe a fifth of the distance down, it then becomes an airfoil blade cross-section. This is an image taken from a 14.3 meter blade that Kieran will talk about in great detail later in the presentation. Codes and standards. So essentially fiber composite materials started becoming of interest to the civil engineering community in the late 70s, early 80s. Probably, and by the mid 80s, there were a number of activities, mostly starting out in Japan. This work was as a response to the Kobe earthquake, and much of the retrofitting that was undertaken then with respect to their bridge and highway infrastructure. The first document of note to describe structural design with polymer composites was produced in the UK by a consortium called Eurocomp. It was a compilation of documents related to how one would design with fiber composites in a civil engineering, structural engineering environment, as opposed to in what was typically an aerospace or mechanical engineering environment. I wrote a book in 2006, which is probably the first textbook related to structural design with FRP materials, and covers reinforcing bars, strengthening materials, and also standalone FRP, fiber reinforced polymer parts. What are we doing in terms of current guidance? The European agency CEN, Center for Normalization, has embarked on an activity to produce a Eurocode for the design of fiber composite materials for civil infrastructure. These are standalone fiber composites, not for those reinforcing bars or strengthening systems. The first part was a prospect, which was published in 2016. This was sent out for comment and received, from my understanding, over 700 comments, and then revised into the second prospect, which was published by the European Composites Industry Association, EUCIA. This is downloaded and freely available. All of these documents are available. Simultaneously, a document was produced in the UK on fiber reinforced polymer bridges, similar guidance for design engineers. Both of these documents include the appropriate, if you will, partial safety factors or material partial factors that would be used in a typical load and resistance factor design procedure according to the Eurocodes. The future of this draft specification is as follows. The technical specification has been written by a committee, including from the UK, Professor Toby Mottram from Warwick University. And this is to be called Design of Fiber Polymer Composite Structures, not fiber reinforced, but fiber polymer, recognizing that both the fiber and the polymer system, in fact, reinforce each other. And this was submitted in 2020. This technical spec is expected to be submitted in 23. And then it will go for the second step of production into a Eurocode, which we think should be published somewhere in 24 or 25. So we're well on the way, and there are clear procedures to follow. Just to give you an idea of what the partial safety factors are, the material partial factors relate to two things. Number one is the uncertainty in the material properties, and that factor can range from 1 to 1.15 to 1.35, depending on how the material properties are obtained, either from testing or all the way over to theoretical predictions. The second in the partial factor is the uncertainties related to the production method of the composite, and this can go from 1.35 all the way out to 2.0. These characteristic values that are used together with the material partial factors are defined as the 5% fractile of the material property value. And this is a procedure following a standard Eurocode characteristic value determination. Just to give you a sense of if you apply those factors, The worst case would be a factor 2.7. Inverting that gives you a 0.37. In other words, you're utilizing about 37% of the capacity of the material. A best case scenario, you would utilize 74% of the capacity of the material in your material partial factor. But that is not all the reduction that takes place. There are what are called conversion factors. That material factor and characteristic value is again, we would call knocked down or reduced for temperature effects, for humidity effects, for creep effects, and for fatigue effects. This gets fairly complicated and depends on the actual application you are interested in. So let's say that factor can get knocked down another perhaps 50% or 40%. So your worst case would be somewhere you'll be operating in about 15 to 20% of the ultimate capacity of the material. In your best case, you might be operating in 30 to 40% of the material capacity. So there are, in the existing code, significant factors to enhance the safety of design with fiber composite materials at this time. One expects as time goes on, these factors will be reduced. And this is not considering the load factors, of course, that are applied to the other side of the load and resistance equation. So what's the problem? What is the wind blade material quantity in the UK? So looking at installed capacity up to 2021. So this is the current information as of the second quarter of 2021. These are the statistics. Currently, the UK in the bottom, in the top left, up to 2021, has a capacity of, it's covered by my, covered in the slide, but the cumulative capacity in the UK is somewhere around 20 gigawatts. This translates into blade material. Here we got, here's the cumulative, cumulative capacity in thousands of tons of material from 20 to 21 installed would be this, and this would be the material coming out of service, offshore and onshore. I'm sorry, these are the same slides. We have coming out of service, not much now, right? Because we're assuming, and this is an assumption that is quite common, that the turbine is designed for a 20-year life, and we can use a conversion of 10 tons per megawatt. This is also subject to some debate because many turbines have lifetime extension now, and many are coming out of service before their 20-year life due to a repowering activity. But assuming 20-year life and 10 tons per megawatt, 2024, we're talking about 10,000 tons. 2020, 2030, which is not far away, we've got 50,000 tons of cumulative material that would be coming out of service in the UK. That just gives you an idea. If you cannot send these to a landfill and you cannot incinerate them, you have to recycle or repurpose them in some way. There have been a number of ideas relative to recycling proposed over the years. Most of them include downsizing of the product, either grinding it down and using it as a filler, or going even further to chemical decomposition called pyrolysis or pyrolysis heat treatment to burn away the resin and recover the fiber for secondary use. Those are mostly still in either the non-commercial area or experimental area. So what we are talking about is repurposing the blade. Taking the blade and using it for some other purpose in civil engineering analysis. Having shown you the pictures of the blade, both from the inside and the outside, as a structural engineer, and I'm a structural engineer, Kieran is a structural engineer, you recognize immediately what you need for this in engineering analysis. And it's non-trivial You need the external geometry. So you need the airfoil shapes along the length. The blades bend and twist along the length. You need an internal geometry. You need to know the location and the thickness of the caps, the webs, the shell sandwich panel along the length. You need to know the material types, typically glass, polyester, and epoxy. And you also need to know the laminates which make up this material. You need a mass and volume fraction. So you need to know the material and where it is. Then you need to know the strength and stiffness of that material. And then you need to know, for structural engineering analysis, and that is typical how structural engineers work, you need to know global blade structural properties. The flexural stiffness in both directions. You need to know also the principal axes. You need to know the shear rigidity or stiffness, and also the shear stiffness with respect to transverse loadings, because in these fiber reinforced composite materials, a shear deformation can be significant. So you might say, well, why don't you go to the manufacturer to get this information? Well, the situation is not as simple, because manufacturers of blades regard all of the information as proprietary. So no manufacturers of blades are prepared to give out this specific exact information as to the material types, the internal geometry, the external geometry, and the strength and stiffness of the laminates that are used to build the blade. In fact, they never test for these from a full-size blade. They develop the material types from doing proof panels on laminates, testing them, building a full-size blade, and then certifying a full-size blade according to an International Energy Agency, International Electro Agency, IEC, Electro Commission, test method to test the entire blade. Neither do blade manufacturers and or designers of blades ever determine global structural blade properties, as would a structural engineer for designing, say, a frame structure. Because all of these designs are done using the finite element method, as you would imagine, for these complex shaped structures, both varying in geometry and material type throughout their length. So in fact, they don't even typically know where the centroid is or the shear center, because this is not a significant piece of information that is needed in 2- or 3-dimensional finite element analysis. However, when we do, as we call it, one-dimensional structural engineering analysis, we need these one-dimensional properties for civil engineering. And that, once again, is not trivial to obtain. We have worked for the last 4 years in our Rewind group because we recognized this very early on, after having lots of brainstorming sessions with things we could do, that until you know the actual geometry and know the actual properties, you cannot really design anything from an engineering perspective. So drawing a sketch of a repurposing project is nice, but doesn't get you any further than a rendering or sketch. So we have developed a procedure to extract all of those pieces of information, going from LiDAR scanning of the blade, both inside and outside, some minor destructive coring of parts of the blade to determine thicknesses and materials, and then a code to develop the structural properties that can be used then in any conventional structural engineering analysis program, such as SAP, RISA, any one of the frame programs you might want to use. So now we come on to examples of engineering analysis. I will very briefly describe first the first work we did, which is using a blade section for a roof of a 40-meter squared affordable house. That was a finite element analysis done at that time, because it is a shell type structure, this roof. We will then look at a structural analysis of an entire blade used as a 230 kilovolt transmission pole, which is actually a project we're working on currently in the United States and will be installed sometime in the next year. And then the design and analysis of a pedestrian and cyclist bridge for a greenway, which is the bridge that is being built in Cork that Kieran will take over and describe. This is the rendering, as we say, the envisioning of a potential use of a large wind blade. This is a 100-meter blade. At the time, there was no existing 100-meter blade when we did this in 2014, 2015. But there were models of 100-meter blades that had been produced by Sandia National Labs in the United States, and also a very effective code to produce geometries and layups called NUMAD. This is downloadable from the National Renewable Energy Lab, NREL, in the United States, very easy to find. And from that, we extracted real geometries of the actual blade. So while these are renderings, the geometries of the parts are exact, if you will, with respect to the actual blade. This is the blade as it looks. This is 100 meters long. And I've described the various parts of this blade. This blade was designed to have a carbon fiber spar cap, in fact, that was needed for the stiffness of this particular structure. Some of the new carbon fiber 100-meter blades that are 100 meter long are also using carbon fiber in parts of the spar cap and other parts, and a foam trailing edge. This had 3 webs as opposed to 2 webs. This third web is quite common to see to support this large panel, this trailing edge panel, and typically only exceeds about a third of the way down the length of the blade. Just to give you an idea of the analysis that we did, so this is the roof part. This blade is so big that if you cut it in the transition region, let me just go back, this transition region is about 7 meters wide. These are enormous, these blades. They really are enormous. This is 7 meters wide. You can, well, make a house out of it, as you've seen. But here we just use half of that transition region to build a roofing system, which is about 4.5 meters wide and 8 meters long. We used the LS Dyna finite element code to look at basically stresses and displacements and behavior in the different panels and in the different layers of the fiber composite material. So, of course, with the finite element code, one can dive down into all of those details. As one knows, with the finite element code, you've got to know what you're looking for and know where to look for it many times to find the appropriate and relevant information that can be used for structural engineering. A paper that is listed in the reference that follows describes how the hand calculation of the same parts of this roof section was done and compares it to the results of the finite element analysis, the hand calculation being one-dimensional structural analysis, as structural engineers often do. The second example, quickly, is what we're building, as I said, in Kansas in the United States. This is a blade pole, a pole used as an electricity transmission pole, not distribution. This is a transmission pole, which is going to be about 120 feet high. The blade is a GE 37-meter blade, and we are at the point now of actual detailing and construction of this blade using full-size parts from transmission hardware. We've done for various cases of these, and these papers are also in the references listed, using our blade machine, extracted the section properties, and done, as you see there, conventional structural engineering analysis for the appropriate load cases for electricity transmission lines. These are not the standard load cases that are used for buildings, and there is a code both in the US and in Europe for designing transmission structures But that gives the load cases, right, and the factors required for those loads. Just to give you an idea, one can plot flexural axial stresses along the height, and one can plot shear stresses. Interesting thing on the left, you notice that the maximum stresses do not occur at the bottom near the ground. The maximum, as you would expect with a cantilever structure, because the section is increasing towards the ground and the thickness of the material is increasing towards the ground. So in fact, the most critical parts of this are up near the top of the blade where the fixtures are attached, because the section is thinner there and the material is thinner there. This is obvious if you think about it as a structural engineer, but needs to be kept in mind that, of course, any stress analysis of a non-uniform section has to take account of the structural properties as they vary along the length. The blade bridge, very quickly, this is something we started about in 2016, 2017. We published a paper in 2019. We will be publishing and presenting a paper at the Transportation Research Board in Washington, D.C. In January 22 related to the work that Kieran is about to describe very shortly. Blade bridges can be of different sizes and different spans depending on the blade you use, and they can have various different geometries. We decided initially to start with very simple, if you will, mass market bridges. One can envision all sorts of fancy suspension bridges, arch bridges, all sorts of funny systems or interesting systems. But in fact, if these are going to use up a large quantity of blades of any type, there will have to be a relatively simple mass market application of these. This was the preliminary concept that we started with. And this is some of the preliminary analysis that was done for, once again, the same thing, the stresses and displacements along the length of the blade. This was done for a moving load, so you also have to take into account a moving load on a variable cross-section. And this is an example of a cross-section with a deck system. I am now going to turn this over to Kieran. I will mute my microphone and let Kieran unmute, and he will continue from here on out.
My name is Kieran Ruan. I'm a lecturer in Munster Technological University in Cork, formerly Cork Institute of Technology, and I'm lecturing in bridge engineering and design and things like that. I'm a bridge engineer by background for many years, more used to probably designing steel and concrete things and FRP things. Now, to give it a little bit of a geography lesson, briefly, Cork is located in the southwest of Ireland. We like to think we're at Central Universe, but as it transpires, most people don't know what where Cork is. So that's just Cork there, about 2.5 hours sort of south of Dublin. Next slide, Larry. Now, the project I'm going to talk about more specifically is the conversion of an old railway line between the village of Midleton, town Midleton, and the coastal town of Youghal, beach town, in east of Cork City. Now, in Ireland at the moment, there's a big rollout of what we call greenways, which are kind of dedicated pedestrian cycleways, and there's hundreds of kilometres of greenways planned to be rolled out in the coming years, and quite a few. It's a very active part of our infrastructure rollout at the moment, and so much so to the point that the government is granting significant money towards greenways, and has taken a kind of policy decision that in terms of infrastructure spending for transport, it'll be 2-to-1 public transport in terms of greenways and railways, things like that, buses versus 1-part funding on roads. So road funding is being, I suppose, two wheels good, 4 wheels bad type thing is happening at the moment. The car is being less prioritised than it used to be. So the distance from Midleton to Youghal is about 25 kilometres. It was a railway line that was constructed around about the 1870s onwards, and in its heyday it would have been very popular. It would have part of the overall Cork to Youghal and onwards rail connection. would have, a lot of car people would have gone their holidays in Youghal and taken the train and whatnot. And in subsequent years, it became very much a freight service for a few industries located in Youghal and whatnot, and kind of fell out of use and went out of use in the 1980s. Next slide, Larry. So what you see here is that is the state of the railway line at the moment, following a bit of site clearance works. As you can see, the rail line has been lifted up, and you're left with the railway corridor left in place. And the Greenway, when it's finished, will have a cross section of about 4 meters, 4 meters cross section, and so it'll be combined cycleway, pedestrian way, and again, these have proven very popular in Ireland. There's been a few significant ones built in recent years. Now, Cork County Council are the client on this job, and they've been very, very helpful and accommodating to us in this project, and we're very grateful to them. They're facing, I suppose, the enduring challenges of restoring an old infrastructure line. So there's plenty of tired and old and disrepaired bridges, new bridges to be built, bridges to be redecked, and all that type of thing. We first approached Cork County Council a few years ago about the possibility of allowing us to build a blade bridge on the Milton Youghal Greenway, and they engaged and were very happy with the idea, actually, in fairness. And through a number of various studies, we identified this particular structure as possibly a candidate structure. It's located about 2 or 3 kilometres east of Middleton, in a townland called Roxborough, and it's an old railway bridge comprising of 2 wrought iron beams. It was timber decking in the past, built on cut stone masonry abutments, and it seemed like a good candidate. The structure itself spans over an overflow or a flood channel from the Dungorney River, and this whole area is quite it's a local area to Jameson distillery. You might be familiar with Jameson's or national whiskey, perhaps. So a lot of the ground here goes barley and gets used in the whiskey industry. That's just an aside, really. And the next slide will show, it's a video, Larry, so you might need to press once again. So this shows the condition of the existing abutments as they stand. You can see in the background there's just a temporary haul track for the construction of the Greenway. Now, Larry, I think if you press once more, it should, yeah, that's it. So you just see the abutments themselves are generally limestone abutments, cut stone, about 750 wide, and this engineering brick on top there. So in general, that's certainly below engineering brick level. The abutments are in solid condition. You can see an old paved riverbed there as well for the overflow channel. Next slide, Larry. And just in general context, so this if we were to use these abutments, the general arrangement here would be that the span is about 5 meters, give or take. The width, the structure, the width of the Greenway is 4 meters, but there are a number of narrow structures on the line, so it would be possible to locally, provide a slightly less width, lower width than 4 meters. But the idea basically is to provide 3 to 4 meter clear width, and the skew of the bridge is generally just shy of 18 degrees. Thanks, Larry. And I suppose more typically, we're very large and well-established concrete industry in Ireland. So the original plans for this bridge were something along this kind of scale, to use pre-stressed beam, concrete infill slab construction, maybe with masonry parapets. Next slide. So we presented various ideas to Cork County Council for ideas for the blade bridge. A lot of the images here were prepared by Zoe Zhang, who's a student in Georgia Tech, and who also spent a few months with us, or 6 months with us in Cork on the project earlier this year. So you can see the basic concept there. It's a short bridge, it's only 4 to 5 meters, and we're using kind of the root end of the cantilever and playing around with parapet ideas. Next slide. And there's various other images there, just to get a feel for the structure. Or even next image again, I think it's a few of these images. Yeah, but that's the image of the blade in situ. And then a final image there, Larry. And this then is the finally evolved structure. So in various discussions, various ideas, we decided to use the entirety of the blade so that users of the Greenway would really understand that this is a bridge, generally relying on recycled or recommissioned wind turbine blades for strength purposes. Next picture. Right, so now as Ari alluded to earlier, working with wind blades is complicated by virtue of many things, but also by virtue of geometry primarily. So the geometry, the blade is changing in various different directions. So we're kind of used to working with rectilinear elements as steel and concrete engineers. Dealing with the blade itself provides its own challenges, not only to do with shear centers and all the different structural aspects, but also, again, just to do with geometry. Next image. Right, so as part of the project, the search was on to locate blades which could be repurposed, and the Rewind team, sourced blades which were sitting in the yard in Belfast, and these are Nordex N29 blades, getting ready now for relocating from Belfast to Cork. And one of the things that's quite important in terms of reusing the blades for construction projects is to get a good scan, a laser scan of the elements. So here, just before they're being loaded onto the lorry, there's a laser scan of the external surface being undertaken. Now, we took a number of these blades down to Cork. 3 of them came into the structures laboratory yard in Munster Technological University. 2 primarily to be used, ideally, in the construction of the bridge, and 1 for various tests we're going to carry out, and just helping us really understand what is the strength of these beams, what are they like in terms of deflection and vibrations, etc., and to what extent can we reuse them. So next slide. So this is the blades right up into the yard in Cork just before last Christmas. So we were just digesting what we have in our yard at this stage. And Maggie there's our senior technicians. We were not that FRP as material in the laboratory. We did a number of kind of training sessions with the technicians in Georgia Tech, just in terms of how to handle material, how to cut the material, prepare the material, and whatnot. And this is our first attempt at cutting the blade. You can see, just as an aside, that the blades obviously had been sitting in the yard in Belfast for some period of time, and had basically algaed up, or they just took a coating of algae on them and whatnot. But it didn't take that much effort just to clean the blades down. As Larry mentioned earlier as well, on the exterior surface, the blades are actually very smooth. They're nice things to touch and feel. There's a high kind of tactile quality to them, and we were keen to kind of incorporate that part of the artifact of the turbine blade into the design, that people could actually touch and feel the blade and see the high quality of its manufacturing. Next slide. Right, so this is the first piece of blade we cut. It only took a few seconds, just a general console. You can generally see the bits and pieces of construction that Larry alluded to earlier. You've got the leading edge on the right hand side, the trailing edge on the left hand side. You've got the webs, your kind of vertical members, as we look at there, and then the spar cap, which is that part of the blade skin between the webs. Now the webs here have downstand sections as well, so it's kind of a C section bonded to the overall skin of the blade, and that cable or that piece of wire going through the blade is just a control system, just where the older blades used to have a kind of a movable tip in them to improve efficiency, etc. So next slide. Now, we already had undertaken external laser scanning of the turbine blades in Belfast before you get out to Cork. Internal scanning was undertaken again with laser scanning, allowed us to put a full 3-dimensional model of the blade in place. Next slide. And here you can see just, literally it gives you the top left-hand section there is a plan view of the blade. The long section is shown below that, and then the various cross sections. So again, the geometry of the blade is quite a complex thing. It changes as you move along the axis of the blade, and very important for us to get a feel for the geometry before we start designing. Next slide. Right, from the period of, say, January, February up to maybe July, August, we spent a lot of time investigating the blade, doing various structural load tests, designing and testing connections, doing FRP burnout tests to kind of help characterize the material in more detail. So next slide. Right, so we undertook a series of static load tests. We have a test rig in our lab in Cork. Generally, you can apply total of 1,000 kilonewton vertical load. So what we did is we took a 4-meter section of the blade, kind of cut it to suit maybe the size of our test frame more than anything else. And we cut holes in the skin of the blade, passed through box section, steel box section, so we were applying load directly onto the shear webs. And we did essentially a 4-point bending test. And we were monitoring on the right hand side there. You can see a few linear variable differential transducers just to measure deflection horizontally at the top, just in case of top edge buckling in the compression edge, and various vertical displacements in at lower points and whatnot. So the next slide, I think, Larry, is a video. And actually, before you play the video there, Larry, the video is probably about 30 or 40 seconds long, and it's if you look at maybe in the last 5 seconds of the video, you'll see that the far edge there on the left hand side, you'll see the blade undergo a bit of a drop or a failure. And what's happening there is, as we'll see in a second, is kind of separation of the web. There's about 9 tons on the blade near the end section. Yeah, so you can see here that's the point where we undergo a kind of separation of the web from the side of the blade, and that's a failure then if it the test section. The next slide, Larry. So on the left hand side there, you can see kind of the before and after shots just at the bearing end of the blade. You had separation there of the shear web and the downstands from the side of the blade, and a more detailed then on the right hand side. And that was, you saw that in the last 3 or 4 seconds of the video there, where you know, it sheared and it dropped at that point. Next slide. Now, once we had the blade demounted from the test rig, it was a question just of basically, you know, taking sections through it and really tracking the damage and seeing exactly how the section behaved and to what extent the damage was localized at bearings areas or more generalized into the section. And what we were finding basically was that you know, the failure was very localized to the bearing areas. On the most right hand side there, you can see that there's a longitudinal crack running along what might be the leading edge of the blade, and that extended maybe 300 or 400 or 500 millimeters around the bearing area support, and then the web as well had separated from the skin. Next slide. So the structure at that point, or the, you know, had undergone, it took about maybe well, just shy of 90 kilograms or 9 ton, and then damage occurred and unloaded, and, you know, a bit of creep movement and whatnot. In general, that's that part of the blade, the kind of smaller section of the blade, it took, generally speaking, about 90 kilograms total load before it failed. All right, next. We subsequently then cut up and we did a series of connection tests. And with the connection tests, we're mindful that we have to have, you know, that, you know, the deck of the bridge is decided. So we're just playing around with various connection types. We tested 3 connection types in total. The first one was just with normal grade machine bolt. And our test setup there is just an angled section bolted onto the side of the blade, and then a single vertical load pushing down on the angled section. The second test was similar size and grade of bolt, but this then was a blind bolt, which is a proprietary system, a proprietary bolt system, which is used for bolting through things like hollow box sections where you can't get access to a nut to tighten the bolt on the other side. And we also looked at 12 mil diameter threaded bar passing through the structure of the blade in total, and in actual fact, all these loads, all these connections, you know, they were found to be taking typically 5 to 6 ton before failure. Generally, failure was associated with the bolts more so than the material itself. Although in the test of the threaded bar, there was an element of bearing through the material, the FRP material. Next slide. All right. So this is just a view of the blade after the first connection tests, and inside and outside. You can see there that there was no apparent surface damage at all around the bolt holes. So we were quite pleased that the materials have behaved very well in that situation. Next test picture. This then is our threaded bar. Now, in this location, we decided we would pass the threaded bar through the blade itself, and in this case here, because we don't have the ticker section of where the web downstand is, we'll see that the threaded bar was able to cut through the material a little bit, and so we got bearing kind of movement in the holes themselves, and a bit of bending in the thread bar. Next slide. So you can see there that the thread bar under 5-6 ton of loading in total on the connection has moved down through the material somewhat. And if you see on the right hand side there, the thread bar also has suffered its own little failure as well along the shaft. Next slide. These then are the blind bolts. The blind bolts is a proprietary system where the bolts are common garden bolts in some respects, but they have a little piece of metal that drops from the shaft to the bolt to allow you to gain purchase on a surface that you can't otherwise access. These are produced under patent by the Blind Bolt company, so we're quite keen to test some of these. And if you see the next slide, these are the blind bolts. Again, we had no surface damage at all on the FRP blade under that test, which again you can see there to about 5.5 ton. If you look at the lower blind bolt, or in fact both blind bolts, you can see there's a bit of bending in the shafts of the bolt. So again, the bolt was failing before the FRP in that case as well. Next slide. Then as Larry mentioned as well, like we one of the problems we have, I suppose, with repurposing wind blades is that we don't have any information from the original blade manufacturers for their own reasons. So between laser scanning, measuring, calipers measuring, and doing all sorts of things, trying to get as much data as you can, really it's a question of accumulating as much data as you can. When Zoe was with us from Georgia Tech in the first 6 months of the year, she did a lot of work using FRP burnout tests, and the process in this particular test is that you cut tokens out of the blade in various locations where you might be interested in the number of plies of fabric that you use, etc., and then you take a single one of those pieces. It goes into a high temperature oven, about 600 degrees for maybe an hour and 20 minutes thereabouts. That has the effect of burning off the polymer resin, and then you're left with the various original layers of ply, which you can separate out. You can check the orientation of the fibers in each layer. You can measure volume fraction, etc. And all this information is very important to help build up a thorough understanding of the blade. And if you see the next slide, that work primarily leads itself then into producing accurate FEA models of the blade itself. And this particular work was undertaken by Dr. Russell Gentry in Georgia Tech as well. So taking our data recorded it from our physical testing and burning and measuring in Cork, and working with the team then in Georgia Tech to produce accurate FEA models of the blades to help us really understand and so it's guarantee the client that what we're doing is structurally sound and fit for purpose, etc. Next slide. Right, so we move on to design development now. We're currently kind of in an advanced stage of design development. Just an overall timescale, the Midleton Greenway, it's expected that the first part of the Midleton Greenway will be opened by Easter of next year. And we're working hard to maybe deliver this bridge in the coming weeks and months, really, certainly before Christmas. And this is just going to be a 3D render, and I've just acknowledged Dennis Cronin has particularly helped us in producing our drawings and working with the difficult geometry with the blades. But the general concept here is like, and this is, this was design evolved through several client discussions and trying to bring everybody along with us with the design development. You can see on the right hand side there, we have the root of the blade kind of projecting beyond the end of the bridge. And that was a decision taken with the client, who was very keen that, that as users of the bridge will walk along the greenway, that there'll be no uncertainty that these are certainly blade bridges, or these are former wind turbine blades now being used as bridge deck elements. So we're projecting out, and we're also continuing the blades on, partly buried in the ground, and they'll have concrete pads which are shown there now just to stabilize them at the ends, just for any vibration that might occur when there's people walking on the deck. Next slide. Yeah, and again, just dealing with the blade geometry. So we're achieving, like, we have this 18 degrees skew, which is kind of an awkward thing to play with further complications, but most bridges have some degree of skew in them. So like, we're, I suppose, 18 degrees skew, where we're getting a clear width of 3.5 meters through the bridge deck. Next slide. So next slide there. Right, and I suppose the construction process, right? Let's say as it's being developed now for the blade bridges, that we'll be preparing the abutments, the existing abutments for reuse. Those abutments are 750 thick, and they're dressed limestone. So we're satisfied through qualitative analysis as much as anything else that they're fit for purpose for taking the new deck. So we'll be pouring an initial kind of bearing plinth, and we're making bespoke steel cradles for the four supporting points of the blade, and those supporting cradles will be cast into the first pour of concrete on the abutments. That's the darker grey area on the top left corner. Then we'll have divvy-dag bars, or high tensile bars, just drilled through the blades at the right location, so that when we come on site, we can land the blades, each blade, or the completed bridge deck. We're still debating which completed bridge deck are lifted in pieces. So they'll land on the protruding cradles, and then there's a final pour of concrete to lock everything in place, so that we're calling these the pilasters. That these four high quality concrete finished pilasters will form the ends of the entrance into the structure. Next slide. And the structure itself is going to be, as the deck structure itself will be a steel structure, and it's just a series of I-beams. Now, much discussion in recent weeks about the type of deck finish to use. We were looking at various options, including GRC, fiber reinforced concrete planks, in situ concrete, steel plate with an epoxy resin, like a Bridgemaster finish. And after much discussion, we're going to use a steel plate deck with a Bridgemaster Sterling Lloyd type finish on it to get the final running surface for the deck itself. So next slide. Now, parapets, you would have seen in earlier photo montages that we have some ideas on parapets, but we're engaging very tightly now at the moment with Cork County Council and their landscape architects, the Paul Hoggart company, in developing parapet solutions for the bridge. So there's various ideas in play at the moment. If you go on to the next slide there, perhaps, Larry. And this is kind of a favoured solution at the moment, which kind of mirrors the blade profile through the railing of the parapet. And the parapet itself can be either stainless steel or galvanized steel or weathering steel. We've yet to make those decisions, but those decisions will be made quite shortly. And like all cycleway pedestrian bridges, the parapet height from abutment to abutment will be 1.4 meters high from finished deck level, but we can taper it off then once we're off the bridge deck. We want to, because we've there's nothing to protect. There's no need to protect the approach cyclists at that point because we're on flat ground. Next slide. Right, Larry, I might hand back to your good self for acknowledgements.
Thank you, Kieran. Can you all hear me? Yep.
Yep.
So we've got a large group, probably 30 to 35 people working on this activity in the 3 different jurisdictions. The Blade Bridge team is led by Paul Leahy at University College Cork, includes Kieran, Russell, myself, Angie Nagel, Zoe Zhang, An Hin at Queen's University Belfast, and Mario Soutis, who's a professor there. The Blade Pole team is down at Georgia Tech, includes Russell, Tristan Aladad, Amar Alshanak, PhD student, Yulisa Henao, PhD student, Angie Nagel from Cork, Chloe Chanicki, and John Respit. We have a team working on the catalog, have you seen? We have a team working on what we call our Blade machine, which converts those LiDAR scans and other investigations into a model of the blade. We have a group that does our GIS modeling up at Queen's University Belfast and helps us to predict where the blades are coming from and when they are coming out of service. The key principal investigators on the project have been myself, Russell Gentry, Paul Leahy, Jennifer McKinley, and Janfei Chen at Queen's University Belfast. Been supported, as I said, by the National Science Foundation, Science Foundation Ireland, Department for Economy Northern Ireland, Munster Technological University, NL Green Power Logisticus, and Cork County Council. This will be available after the presentation, I believe, on the iStructE website, and you're welcome to look further into some of the details of what we discussed. These publications and other presentations are all available on our website at www.re-wind.info. So thank you very much, and I think I will stop sharing my screen and hand that over to you for questioning. Kieran, you want to take some of them? I'll take some of them.
Yeah, well, I might just read out some. You can decide. So the first error was from Georgius, and it says, I understand that the FRP composite wind turbine blades come to the end of their design life, but do they get replaced because they're faulty, or because they just go to the end of their design life?
So I'll take that question. This Georgios, is an interesting issue. It depends entirely on where you are. So what we are seeing in the United States at the moment is a significant amount of repowering. In other words, taking down the original turbine or taking down the original blades on an existing turbine at an existing wind farm in order to replace it with a more efficient turbine, generally producing more power and able to perform in lower wind speeds. That we call repowering. The blade that we are working on in Kansas has only been in service for 11 years, and they're already taking it down and replacing it with a larger turbine and larger blades. On the other hand, we've seen blades in other parts of the world that are being extended. So after the 20-year design life, they are extending them with various solutions, including even lengthening blades. These are all generally fairly expensive propositions and need to be considered and are considered as essentially a financial decision by the operators. The difficulty now is that in Europe, definitely in Germany, in most of the Netherlands and in Denmark, and soon to be in the entire European Union, and I believe this is in the UK, it is illegal now to landfill wind blade materials. It is also not desirable to incinerate them in different places. So we are looking at these solutions. They are generally not faulty, and that is how we can use them in our civil engineering applications. The blades are in very good condition. They are designed typically for 20-year service life. They are taken out of service, as I say, somewhere between 15 and 25, maybe 30 years. They are very conservatively designed, especially the earlier generation blades like the one we're using for the bridge that Kieran is building. That blade was manufactured in 1993, probably been in service for about 15 years, taken out of service. And as you can see, the condition of the material in the blade is extremely good. We are at Georgia Tech doing as received tests on the materials that we receive and finding that there is very little loss of strength and stiffness from the originally predicted material in the blade. Given that it's going to be subjected to, I would call it quasi-static limited dynamic loads in a bridge compared to that in which it has seen in the wind blade, we feel comfortable that these could service the civil engineering community, as we see with those safety factors of down of 10 to 20% utilization of the material for many years to come. We estimate these will be in service for 50 to 60 years following their repurposing.
Thanks, Larry. A question from Finn. He says, how much does a single blade cost to purchase for private use? Is there a resale value that blade companies incorporate into their business model?
There are numerous companies that attempt to sell what we might call second-hand blades. The used blade market, it's quite easy to Google them. These sell for a lot of money. So typically the blades that Kieran was looking at for an N29, an old 14-meter blade, might be selling somewhere between 5,000 and 10,000 euros. However, there's very little market. There's very little market for these blades. And the blades that we were provided with from Everrun were donated. In fact, many companies, many wind farm owners are, let's say, interested in doing something else with their blades and are often willing to part with them for free. The alternative in many countries, landfilling or incineration in cement plants, can cost upwards of 500 euros a ton. Remembering that a large blade is 6 to 7 tons, the blade Kieran is dealing with is 750 kilograms. So as opposed to paying to dispose of the blade in that way, it is possible to obtain these blades from a farm owner essentially for free. And that's how the business case can be made for these repurposing projects.
Yeah. Thanks, Larry. Martin asks, if the blades are required to be used in their entirety for bridge construction, have the logistics of transporting such massive structures to site been considered? For a bridge requiring such a large crane, it will be typically be built adjacent to the final bridge location before being moved into position. I'm actually let me start off the answer to this question, Larry.
Sure.
Yeah, personally, when I was involved, consulting engineer for many years, and we used to do a lot of work helping wind farm companies move blades around the country for wind farm construction. And we were moving blades around the country on often rural roads, blade lengths up to 50, 55 meters. Now, obviously, that took a lot of logistic planning and, moving street furniture and taking down people's walls and putting them back up again and whatnot. But it can be done. The blades, I think, blades up to 100 meters, I presume, are more for offshore use, I'd say. And then in terms of logistics for building the bridge, yeah, certainly, like in our bridge, we have a small bridge. We're taking baby steps with this, trying to build our first bridge. We'll probably be able to build our bridge using just, several kind of decent sized crawler excavators on site that will probably be lifting things for us. But we're debating whether to put our bridge together in its entirety in the fabrication yard, put it on the back of a flat lorry and bring it down, lift in one go, or which the site would prefer, so we brought it taken down in pieces and put it up in pieces like a Meccano set. But yes, I mean, bridge building, as you point out, generally requires large cranes anyway. So I think we will be able to get these large blades around the country because we're doing it already for wind farm construction. That's the general point I was going to make.
Yeah. Just to continue on that is the big difficulty with building a wind farm. The logistics of moving the blade is typically about a third of the cost of the blade itself. So as soon as you move beyond a standard length truck, 17 meters, 50 feet, you are into specialized vehicles and permitting. And depending on the terrain, if it's nice and flat, even then you've got a problem with roadside hardware with low bridges. So our philosophy is typically to try and use the blade as close as possible to the wind farm from which it's being decommissioned, if it is longer than 50 feet, 17 meters, or to section it and then use it elsewhere in a reconnected fashion. The issue that is now occurring with offshore blades being 100 meters long, all of these are being manufactured right at the coast where they can be loaded directly onto barges and taken out to sea. So there is almost no consideration of moving these extremely large and long blades over land anymore. But those are, in terms of operation, 30 years from now, we will only be seeing them coming out of service. We are talking about blades that have been installed in the past 30 years that are coming out of service in the next 30 years. So that's really the issue.
Yeah.
Go, Kieran.
I'm sorry, and that kind of leads on to David there has raised a few questions, and you've kind of touched on it in earlier responses. But David asks, what is the operational life of modern turbine blades?
Yeah, I think we've touched on that. It's very much location dependent and an economic decision typically of the wind farm owner and the designer.
And Dave also asks, how do you actually inspect turbine blades in use?
That's a question on the turbine blade menu. There are many companies now that offer live drone inspections of turbine blades. They're essentially looking for defects on the outside that may be caused or damage on the outside of the blade that is caused in service. The largest culprit for damaging blades is lightning. Lightning strikes on blades, seeing they stick up high and are the significant damage to blades. There are lightning protectors and pads that are used to ground the blades, but nevertheless, lightning strikes are the most common damage to blades. There are other in service, usually due to manufacturing defects that get discovered in service, and these are usually determined from exterior inspections using drones and photogrammetry, many thousands of photographs. There are also companies that are now beginning to monitor blades in service with strain gauges, accelerometers, and devices of that type to determine whether or not there's been a degradation in properties or any type of damage, structural damage to the blade.
Thanks, Harry. And another good question from Dave here, which is quite pertinent question. Can the new structures made from decommissioned blades be insured? I might just answer that briefly. That we've had discussions here with the college insurers, Munster Technological University insurers. We explained to them what we're doing. They've been talking to Cork County Council insurers. So the insurance people seem to be on board with us at the moment. Now they know that, I should have said earlier actually, that when we build our bridge and before it goes out to site, we will be doing a full-scale load test on the completed bridge deck by using bags of aggregate and bags of sand to stipulate loading. And actually, that's as a complete tangent, I forgot to say, mention design loading as well. The bridge is designed for Eurocode 1 Part 2 loading, generally pedestrian loading 5 kilograms per meter squared, plus the accidental wheel load case or the accidental vehicle case, which is a 12-ton vehicle effectively. So back to your question, Dave, about insurance. Look at we've been engaging early with our insurance people, and nobody's raised a red flag yet. So I think they seem to be happy enough with what we're doing anyway. Philip asks, in order to compensate the absence of knowledge related to specific GFR beetle laminate characteristics of their decommissioned blades, were you considering to simplify performing residual edge-wide stiffness testing for each blade to guarantee its safety and loading capabilities? And I suppose what we're doing, Larry, and you'll probably come in more detail on this, but we're kind of doing a mixture of both really at the moment. I suppose we have the benefit that we have a test rig that we can really test, and we have spare blades as well that we can test failure and all the rest of it. And we're also drawing on the detailed expertise that Rewind team has built up over recent years in doing a burnout test, material characterization test, and onwards into FEA. So we're doing a kind of mixture of both FEA and full-scale load testing in our case. Larry?
Yeah, I would add to that given that there are many blades of a given type and design, for example, these LM Danish company manufactures blades, the 13.4 meter blade that Kieran is working on, thousands were produced with the same design, essentially. So once one has done a detailed characterization of the blade, one then needs to, as Philippe suggests, what we plan to do is do proof testing for the particular situation we're interested in. So if it's being used as a pole, you proof test maybe in two simply supported configuration, as Kieran has done. If you're using it for a pole, you would proof test it in a cantilevered condition. But a proof test will only take it to the service load. But this is typically done, for instance, for timber transmission poles. Every pole is proof tested before it goes out into the field. The same for composite transmission poles. So that's the philosophy. You do a very in-depth characterization of one of a type, and then hopefully you do only proof testing and exterior observations, if you will, to see if there's damage in the blade before you go and do it. So you wouldn't have to do testing on every blade of every type, we feel.
Thanks, Larry. I've got questions here from Aisha, and I hope, sorry, Aisha, I mispronounced your name. Shouldn't the government be doing more to reduce the amount of blades ending up in landfill? You'd probably say yes, Larry, to that, I think.
What should I say? Yes?
Yeah, I think so. And yeah.
I'm not the government.
Yeah, but it's interesting, guys. It's a general point, really. It's a big push to get more renewable energy on the grid, and like there are costs, environmental costs to that. As we're seeing, as we're dealing with here with the recycled blades, whatever. Aisha also asks, wouldn't it be more sustainable to use a blade material that can be easily recycled? Which is a good point.
Good question. So this is the latest activity in the wind blade manufacturing community, and that is to develop blades or to build blades using what we call thermoplastic polymer materials. So thermoplastic materials can be reheated and melted and reformed into different shapes, and it would be easier to remove, to recycle these materials in that fashion. The current blades are built with thermosetting composites that cannot be reformed or melted down and made into pellets and then reused in something else. So they can only be, if you will, ground up, burnt, or put into a landfill. So this is the philosophy being adopted by the large wind blade manufacturers at the moment, to use resins that can be reformed. Now, whether or not that is economically viable to recycle them in this way is another question that will be decided, unfortunately, only 30 years from now. It's unfortunate that these studies are not done at the time, as no studies were done 30 years ago for the original thermosetting blades that were made. There is little being done now to validate the assertions that thermoplastic resins are going to make recyclable blades. But it sounds good at the moment, in my opinion.
Thanks, Larry. Just two final questions, and both related to durability. Mina asks about the ability of the sections to serve after being used in the hard-duty wind farm environment where it's been subject to strong wind fatigue. And even if one was tested and was fine, can we be sure that it's valid on the rest of it, that it will remain durable, I think is what the point is. And what is the expected lifetime of structures based on such reused elements?
So I alluded to this a little earlier, in the sense that blades are taken out of service due to their design life, which is originally an extremely conservative estimate of the capacity. Of course, there is a well-known problem with fatigue of glass reinforced composites. We test the materials for the as-received blade. We expect, and we have noticed that generally after a blade has been in service, it is felt that there's maybe a 10 to 15% drop in ultimate strength due to the fatigue loading over millions of cycles as a wind blade. And as I alluded to earlier, the safety factors that we then putting on the as received materials that would be tested from these blades are large, as is typical in most civil engineering designs, very different from mechanical designs, mechanical engineering. So we're confident in the ability. We will be doing more fatigue testing on the as received materials to determine long-term fatigue effects and predict long-term life. But at this time, we believe that there will be no problem with structural capacity over the extended lifetime that we envision, which is 50 to 60 years or more, as long as the bridges are maintained, as are most bridges maintained. I think the second question, the last question relates to this as well. How durable?
Yep.
Yeah.
Go
ahead, Kieran. Yeah.
Well, I was going to say, the final question from Michael there is how durable are their blades and exposed to the alkaline environment of concrete embedments? Very, very good question, actually.
So I'll answer that.
Yeah.
Essentially, we do everything we can to protect any junctions or so any penetrations we make through the hole. We epoxy seal. You do not want moisture coming in contact with the glass fiber itself that is in the blades. So you do as much as you can to protect exposed fiber after you make any penetrations or cuts. That's absolutely critical. Embedding fiber-reinforced composites, though, in concrete is now an accepted technology. And so these are glass fiber-reinforced composite reinforcing bars. And as long as the material is processed effectively and the voids in the material are smaller, and we're talking about voids less than 1%, which is extremely good processing. In fact, these blades are processed to extremely good tolerances in terms of material processing by a vacuum infusion method, and produce composites that have less than 1% voids, which is regarded as an extremely, extremely good composite. So we are not concerned with ingress of moisture or alkalinity into the interior of the material unless it's exposed. So exposed edges and cuts need to be epoxy sealed in general.
Yep, and that's right, Larry. And the other point I was going to make was that, as you mentioned as well, like there are FRP reinforcing products for reinforced concrete available on the market. And the last point, just to wrap up, all the questions are answered now, but just come back on durability. I suppose really this is a bit of a live project for us, so when it's not like the project will end when we install the bridge, it'll become a durability project from then on for the foreseeable number of years ahead, Larry, that's yep.
I think we're at time. The only anecdote I will add to this in terms of a similar environment is using fiber composite in shipbuilding and pleasure craft and yachts. This has been going on for the last 50 years. Those are subjected to extreme environments and fatigue loading that we see in similar to civil engineering. And the biggest problem for the boating industry at the moment is that the boats last too long and they can't sell any more new boats. So we hope that will be the situation with our bridges as well.
A nice note to finish on, Larry. And like I say, I think we managed to meet on time despite our my technical difficulties at the halfway mark. But,
well, thank you, everybody. And this, I believe, will be available on the iStruct.e website, and I believe as a recording, and will probably be on YouTube as well. Maybe we'll cut out the technical difficulties that took place. But thank you, Kieran, and no worries about that.
Thank you, Larry.
Feel free to contact us at any time if you're interested in more information about these projects. Thank you very much for listening.
Thanks, everybody, and good night.